One important thing to be able to model is when one oscillator might be interacting with or impacted by another oscillator. In some species of fireflies, the timing of the light emission seems to be impacted by their perception of the emission of fireflies around them. And so the phase of one oscillator is being impacted by the phase of another oscillator. With neurons firing, the firing of one neuron might impact the timing of the firing of another neuron. And so we might make a simple model of neurons where we're thinking of a phase. At this point in the phase, it fires, it's going around its phase loop. And depending on the phases of nearby neurons, the phase of our neuron may change. An application of this might be trying to make a model of jet lag. Some work modeling jet lag has worked to have the circadian rhythms interact with a periodic forcing coming from the sun. Generating circadian rhythms themselves, in turn, requires oscillator models. If I wanted to make a model of a number of interacting oscillators, say n interacting oscillators, each of those n oscillators would have a phase angle, theta 1, theta 2, etc., up to theta n. That would be the phase of each oscillator. And then the rate at which the phase angle of one oscillator is changing might depend upon, that might be some function that's specific to this oscillator that depends on the phase of this oscillator as well as the phase of the other oscillators. So for each oscillator, there's some model of how it's the rate of change of its phase that has its own particular individual function that depends on the phase of all the others. Of course, the first simplification that we might make is that in our system, all of the oscillators might be the same. And so all of these functions might be the same. But whatever simplifications we think about making right at this moment, we haven't worked with systems that have more than one state variable at this time. And so we're not quite ready to think about a system of coupled oscillators. At the moment, even if we can't think about two interacting oscillators where they each will change based on what the other is doing, we could think about a single oscillator that's interacting with a reference oscillator. So imagine this reference oscillator to perhaps be the sun, or this reference oscillator might be an LED light that we've set to flash at a certain interval, interacting with a firefly that actually thinks the LED is a second firefly. So this is a capital theta, this is a capital omega. Our reference oscillator is set to just be going at some frequency. Let's say the model that we're oscillating, our oscillator, is trying to synchronize with this reference. So we're going to model our oscillator, which has phase angle theta, as having some intrinsic frequency, omega, that it would be going around at in the absence of the presence of this other oscillator. And then, in addition, let's say our oscillator can sense its phase difference between it and the reference. Specifically, if here's our phase angle, our reference, capital theta, might be right here, and our actual oscillator might be right here. Their phase difference is capital theta minus lowercase theta. And so if an oscillator is trying to synchronize, what kind of function do we want here? Well, if little theta is behind, I suppose we would want to speed up. And if little theta were instead ahead, I suppose we would want to slow down. Okay, so we would speed up if capital theta is larger than theta. If capital theta is ahead, the reference is ahead. We would slow down if the reference is behind. To think this through, let's think about the phase difference ranging from, say, pi. So capital theta is ahead of theta by pi, half the circle, to negative pi. Oh, wait, pi and negative pi are sort of the same thing, because being ahead by half the circle is the same as being behind by half the circle. And then, of course, they could be at the same spot, 0. So if we're over here, the reference is ahead. If we're over here, the reference is behind. What do we want this g function to do? Well, when the reference is ahead, we want to speed up. So we would want extra extra speed, we want g to be positive over here. So I'll just kind of shade that in. We want g to be somewhere up here. And then when it's behind, we'd want it to be negative. Whatever happens at pi should also happen at negative pi. And of course, when the difference is 0, we're probably pretty happy with g. So we'd be happy for g to pass right through 0. Since pi and negative pi need to be the same, but we're positive on one side and negative on the other, that actually also has to be a 0. And so a function that would satisfy this, that's negative and positive and passes through the right zeros, is the sine function. Let g equal a sine of the phase difference, where a is some kind of magnitude, which tells us how much the oscillator would speed up extra for a given phase difference. We have a model of how it might make sense for an oscillator to respond to a reference oscillation when it's trying to match its phase. And a natural question to ask in this situation is, does entrainment occur? Will the frequency of the oscillator end up matching the frequency of the stimulus, even though they actually had different natural frequencies? The oscillator had a natural frequency lowercase omega, and the stimulus had a natural frequency uppercase omega. Asking the question of, does entrainment occur, is the same as asking the question, does the phase difference ever approach some constant, so that one oscillator is moving around and the other one is moving around with just some modest phase lag in between them as they go around at the same frequency. We'll set up a differential equation for the phase difference itself. So the phase difference is just the reference minus the phase of our oscillator. And if I take the derivative of one side, it's equal to the derivative of the other side. Recall that the derivative of capital theta dot is capital omega minus omega plus a sine. Oh, and the sine was actually already of the phase difference, so a sine phi. And so this simplifies to omega minus little omega, the phase difference minus a sine phi. Let's analyze this system. The first thing to note is that this is dimensional. So let's go ahead and non-dimensionalize. And I know it's dimensional because there's a derivative with respect to time, and it's not a non-dimensional time variable over here. And this is a rate. It's angle per time. So this has units of 1 over time. So this term must also have units of 1 over time. We'll create the non-dimensional time variable tau for this non-dimensionalization because we created a constant capital T naught with dimensions of time, and we'll figure out what capital T naught should be later. I'm going to go ahead and substitute this into the derivative and simplify the expression. Okay, I've replaced the dimensional time with tau times this time constant. Multiplying both sides through by T naught, I have a non-dimensional expression on this side, and so I know that each of these expressions is also non-dimensional. In addition, sine phi needs to be non-dimensional, and so I'm able to identify two dimensionless groups where each of the elements within the group has dimension, but the group itself is dimensionless. For this particular system, it would be convenient not to have a coefficient instead of this in front of the sine phi, and just have the one parameter that's left be right here, so that we'd sort of be moving a constant up and down as we dialed our parameter. Since I need to choose one of the dimensionless groups to set to 1, I'm going to set this one to 1 by letting capital T naught be 1 over a. And so now I've chosen the time constant that I used to non-dimensionalize. I chose that time constant to be 1 over a. The non-dimensional group that's left is capital omega minus little omega over a. That's what this simplifies to. And I'm going to name that mu and write my new dimensionless equation. Okay, my new equation is that the derivative of phi with respect to time is equal to mu minus sine phi. Let's take a look at a few different scenarios for the parameter value. We know that if mu is bigger than 1, there won't be any fixed points. And so in that case, phi prime is always positive, and there's no possibility that this phase difference could ever become constant. When mu is in between -1 and 1, we know that actually there are fixed points, and one of those fixed points is going to be stable, and the other is going to be unstable. Increase, decrease, increase. And so what's happening here is that no matter where we start, no matter what phase difference we start with, our oscillators approach this constant phase difference. And then finally, if mu is less than -1, again, there's no possibility of a fixed point. There's no possibility of phi prime being 0, and so there's no possibility of a constant phase difference. So we have what we could call phase locking. The phase of our oscillator gets locked to the phase of the reference signal with some difference in between them, but I always know the phase of my oscillator if I know the phase of the reference, or we would call that entrainment, and that's happening for this range of parameters. Returning to our dimensional variables, this is happening when the difference in natural frequencies is less than the amplitude of our function g. Something interesting to note is that for at least one firefly species, it's been found that they can actually control their intrinsic frequency, and so they have an extra dial beyond being able to sense and try to catch up to another phase. They can actually adjust their intrinsic frequency of oscillation to make phase locking more possible.